you'll be interested in it too. What do you think? What is this? Yeah. Okay. Everything okay online or hello?
Yeah, we can hear you.
Okay. Somebody is online. Are the slides online? Somebody's saying. Oh, okay. Oh, are the slides online on the website? Okay, they're online on the website, yes. And also you can see the slides as well, right? Everyone online? Maybe not?
Yes.
Okay, good. It's good feedback, even if it's delayed. Okay. Yeah, I'm going to. This was initially intended for a security audience to showcase the problems that we have in architecture. But I think I also expanded towards more on the architecture side as well. So basically, the agenda, the first part of the agenda, computer architecture today, what is it and where it's going? We kind of covered that last week. So I'm going to go through some of these slides very quickly. And then we're going to go through some of the meat of the issues. I'm going to focus on three major hardware issues that I think affect security. Not just security, but a lot of things as well. But the focus of the talk was security. But I think security is also important to look at going into the future. And these are going to be technology scaling problems, growing system complexity, and old methods not keeping up with the system complexity. We're going to pick on one way of doing partial security in existing systems called virtual memory, which is a really terrible way today. You learned about it in DDCA, some of you. We're going to deconstruct it today. Although in DDCA, we can deconstruct it a little bit too. But we're not going to spend a lot of time on that. And then we're going to talk about new architectures and technologies. Let's see how much we can cover. Does that sound good? Okay. Okay, let's jump in. Why do we do computing? We discussed this last time, so I'll go through this relatively quickly to solve problems, to gain insight, to enable a better life and future. How does a computer solve problems? Well, we talked about this last time also. You remember last time? Okay, so I'll go through this relatively quickly. Even in DDCA, we talked about it. So some of you have been seeing it for multiple times, but that's fundamental. So how do you get a problem solved by electrons? We build a transformation hierarchy to enable that today, okay? And we're going to take, as I said last time, we're taking a broader computer architecture viewpoint, which is really spanning all the way from algorithms to devices. And hopefully the paper selections that you are seeing have actually that breadth as well. Okay, we've also discussed this last time, but computer architecture is really the science and art of designing computing platforms, the hardware, the interface, system software, and the programming model to achieve a set of design goals. And again, your design goal may be very different. It could be lower cost on many workloads or highest performance on a very few workloads. It could be basically supercomputing, mobile computing, or general purpose computing, but many fundamental principles are still similar. I heard myself. Okay, everything's okay on YouTube also? Okay. Okay, so basically I'll go through these platforms. You can see some examples, which we did last time. So I'm not going to harp on any of these at this point. We talked about systolic arrays last time briefly, right? These are things that are powering some of the machine learning infrastructure that we have today, TPUs. We talked about some other processors specialized for driving maybe. A lot of these are still neural network acceleration. And we talked about people designing systems overall to actually, basically people really not just designing new chips, but also designing entire systems. So a lot of companies are doing that today for good reason. And this was actually envisioned by research much earlier than companies have been doing. Okay, then we talked about GPUs and more interesting, potentially, or aggressive ways of building chips that are large. I'm not going to harp on these. So people have been building a lot of chips and systems, and processing in memory is another aspect that we have discussed last time. I'm going to go more into processing in memory today, actually, toward the latter part of the talk. Okay, so I think these examples show that things are happening along this direction, meaning people are designing systems as a whole, which includes changing the hardware and changing the software and changing everything in between. Which is good because this is really important for achieving high efficiency, high performance, and high robustness. Maybe the problem is with this room. I don't know. When I come to this room, it didn't feel so good. So I'm going to take my measurement device. And we're going to take the scientific approach. It's looking okay. This is measuring the carbon dioxide in the room. 640 is not bad. It should be around 400 in a nice outside environment. And this number has been increasing over decades in the world. That tells you something. Okay. To get back to the point, yeah, we want to take this expanded view really to specialize the entire system. Okay, what limits us in computing today? We also discussed this last time, not the applications, because people will come up with applications. This is something we have not looked at. Basically, applications are important, and as applications push boundaries, platforms, computing platforms become increasingly strained. And this is going to happen more and more. And we have many metrics to optimize for, and this is part of the difficulty, I think. It's very hard to optimize for all of these metrics. And you can see there's performance, energy, power, correctness, robustness, cost, programming ease, usability, scalability, simplicity or complexity, and who knows what else, right? And clearly some of these are more important or less important depending on your design goals or your system or your constraints. But a lot of these have some role to play. Like you can say, okay, I'm going to design the best hardware, but I'm not going to care about the programmer at all. Then you may end up producing a system that is not programmable by anyone except for a few people in the world, and then your system will die quickly, right? That has happened in the past. Does anybody know about the IBM cell processors? No? These are the first example of multi-core, heterogeneous multi-core systems. IBM designed it for PlayStation, Sony, essentially. And they made some choices that made this extremely hard to program, like no coherence, for example. So the programmer had to deal with all of that. And as a result, you don't see IBM cell processors around today. Well, that's not the only reason, but that's one of the major reasons that if you talk to like people who designed those processors, they would tell you that. Okay, so basically metrics are important. You cannot ignore everything. Maybe we should get rid of this room. Should I admit people? Okay, there's chat, yes. Yeah, maybe we should get rid of this waiting room. Not on my screen. Anyway, yeah. And this becomes harder, especially with complex systems and hardware. As your system complexity becomes larger, it becomes difficult to optimize for these metrics. And I think this is one of the problems that we're having with systems today. Complexity is increasing, and it's very hard to tame that complexity so that we can maximize efficiency. Meaning that maybe we should really take a blank slate approach and redesign the systems from the ground up to be much more efficient. So that's what will bring us to processing in memory and alternative technologies later on. But before that, now let's jump into what I think are three major limiters to computing. This is my personal perspective, of course, based on what I know. But I think there are three major issues that we're facing today. One is technology is not giving us a lot as it used to. Basically, scaling is not going well. It's not going well for performance, meaning in the past we had scaling. Both Moore's law enabled many transistors at low cost. That's slowing down. Transistors are coming at much higher cost today because it's very hard to fabricate them at very small technology nodes. And then Dennard scaling has stopped, meaning when the transistor that you get is not lower energy. Because you cannot scale the voltage after some point in technology node. So you don't get energy scaling benefits, meaning it used to be that you would improve transistor performance and also you would improve power. So you would get both power and performance benefits. Now the power benefits are gone. Performance benefits are still coming slowly. Okay, so this is the technology scaling essentially. It's not going well, so performance is suffering, meaning it's not improving as fast as it would. In the past, there was a time where people used to not care about any of this, what I just talked about, this algorithm hardware co-design. This would be a niche, right? So right now, everybody's doing it because this technology scaling is not going well, because you don't get performance by doing nothing. And that's literally what happened in the past. You had this piece of code, serial, you would do nothing, and the next generation processor improved that piece of code by 50%, let's say. And people got used to it, and now it's changed. So I'm going to talk about technology scaling for robustness especially, and security kind of reasons. At the same time, system complexity is increasing, partially because technology scaling is not going well. We make our systems more heterogeneous and more complex. And once we make our systems more complex, old methods that were designed for simpler systems become much less efficient, and they're not keeping up. Virtual memory is going to be one of the examples that I'm going to pick on. I think you can pick on many other examples. Coherence is another example. Consistency models are another example, which is a mess in general. So there are many other examples like this that we could talk about, but I would encourage you to think about other examples that where old methods are not keeping up. And finally, over here, I think independently of both of these, and maybe related to technology scaling a little bit, because technology scaling has not improved interconnects that much, processor-centric designs are not really keeping up, like meaning data moment really dominates a lot of things. We discussed this briefly last time, but we're going to go into it more. In the end, I think all of these affect the metrics we care about. These are the metrics, and all of the metrics, I would say. Like virtual memory is at the heart of programmability, for example, today, or ease of use. And these, I believe, have fundamental impact on security and how we build secure systems. So I'm going to still keep the security focus a little bit. Okay, so let's pick the first one, technology scaling. So essentially, circuit size and energy reduction, as a result of circuit size reduction, has enabled continuous innovation at all levels of computing for the reasons that I mentioned. You get performance by doing nothing, essentially, almost, at the higher levels of the stack, right? As circuits become smaller, unfortunately, they become less reliable. And more flaky circuits are a problem for robust, meaning reliable, safe, and secure operation. And if circuits produce wrong results, security can be affected, along with other robustness issues like safety, reliability, and availability. Does that make sense? And we're going to hopefully have some papers related to these areas. And you may remember this from DDCA. Basically, we're building infrastructure, and if the infrastructure has robustness problems like this, the infrastructure is essentially useless, right? At least for some purposes. You can come to part of this and jump over it, but you've got to be a good jumper. It's basically useless for what it was designed for, right? Okay, so I think this is a kind of a bit flip, or a circuit producing a wrong result, let's say. And it caused a robustness issue, which is a security, safety, and reliability problem. Another bit flip could happen, then these guys would be very upset soon after, right? Okay, so I think security is really, I think we should really have a more broader definition of security so that we can build much more robust systems that we can truly rely on, meaning these systems will operate. So bridges are maybe not so interesting, right? Because people have been building bridges humanity has been building bridges for thousands of years. And we still didn't get it completely right, as you can see. But they're really a small infrastructure, I would say. The real infrastructure is computing today, and they're everywhere. And computing will really affect everything we do. It'll enable us to go to space, etc. So if we actually have unreliable components, maybe it's not going to go well. I mean, you're familiar with this picture, right? This is a maybe more reliable system than a computer, let's say, computer or machine learning based system that works, because at least this guy over here hopefully has some reason, regardless of the fact that he's Mr. Bean. He still has some reason, I think. Whereas I'm not sure if the machine learning systems that we build have any reasoning capability beyond what they were trained on. Even what they were trained on, they don't have any reasoning capability as far as I understand. Okay, anyway, but these things are going to be everywhere, and we need to have more robust platforms. So I think this is a challenge and opportunity, as we discussed at some point, a robust future. So I'm going to focus on the RowHammer problem, but I'm not going to go into a lot of detail because there might be some papers that will discuss this. We did a lot of work on this topic, but this is the fact that you can predictably induce bit flips in commodity DRAM chips. And essentially, all recent DRAM chips are fundamentally vulnerable to this problem because it's a technology scaling problem. As cell size reduces in DRAM, cells become smaller, cells become closer to each other. They become much more vulnerable to noise. And as a result, it's very easy to change the voltage level or charge level in a capacitor, okay? And this is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability, because once we demonstrated that you could get these bit flips on a real system, not only on an FPGA, but also on a CPU-based system, people said, oh, okay, we would actually exploit these bit flips as we envisioned in the paper. So basically, you can see articles like this. So basically, that's the phenomenon. Let me give you a little bit more detail. If you have memory cells, and this is an array of memory cells, every memory looks kind of like this. Inside each of these rows, you have thousands of cells. In DRAM, that cell has a capacitor and access transistor. And if you want to access some of these cells or one of these rows, you need to activate that row, which means that you need to apply high voltage to that word line such that the cells are connected to the bit line so that you can sense them. This is called activation. Now, if you need to access something else, you deactivate this row, apply low voltage. This is called precharge in DRAM terminology. Now, if you keep doing this repeatedly, activate precharge, activate precharge, activate precharge, activate precharge, enough times before the cells get refreshed, it turns out in existing DRAM chips, you deplete charge in some of these vulnerable cells. And those cells are called RowHammer vulnerable cells. When we wrote the paper, we showed that this is a hammered row. We said that this is a victim row. And we showed that essentially in all chips that were manufactured after some point, you would get this effect. And these were the results. So we said that this is a technology scaling problem because old modules where cells are bigger and cells are far away from each other, you cannot induce these bit flips within a refresh interval. You cannot have enough activations to cause bit flips before the cells get refreshed in the specified standard. But at some point, the number of activations to cause these bit flips became smaller enough than the number of activations you can fit within a refresh interval in DRAM. And as a result, you could actually induce these bit flips with legitimate programs within a refresh interval in DRAM systems. So which makes the security problem. In a sense, there's fundamentally all memory is vulnerable to read disturbance. Whenever you read one cell, you really have some disturbance effect to things around it, right? That's basic electronics, actually. If things are far away, if there's some isolation between the cell you're accessing and the cells that are around it, then this is not a problem. This may be a problem under conditions that are basically illegal, meaning people should not operate things this way, right? Maybe you never refresh DRAM, and then you can keep activating, and this becomes a problem, but nobody does that, right? There's legally, you should be refreshing DRAM to obey the standard. Otherwise, you're not guaranteed correct operation anyway, right? But when things are legal, meaning that you're refreshing DRAM and you're accessing with legitimate access patterns, if you're inducing bit flips, then that turns the problem, that gives us read disturbance problem at a very different twist. Yes, everybody knows about the read disturbance. It happens in electronics, but normally you contain it, meaning solve this problem. The fact that this slips into the field turns it into a real security and safety and robustness problem that people should be worried. And then you can ask questions, of course, why did it slip into the field? But we can talk about that maybe later. So if you have a bit flip like this has implications at the higher level of the transformation hierarchy. And if in the end, it affects the user. So if you get a bit flip, for example, it could cause a silent data corruption, right? Meaning that your data may be corrupted without you knowing it. Or someone can just have this malicious access pattern to actually take over your system. So when we first wrote the paper, we also showed that with this piece of code, x86 code, you could actually induce these bit flips in real chips using real CPUs, using this is a user level program. It has no privilege at all. So what this program does is it basically ensures that you bypass the CPU caches and ensures that you bypass the row buffer over here in DRAM in the same bank. It selects addresses X and Y and basically ping pongs activations to X and Y. And if the chip is vulnerable, you'll get bit flips. Now in the paper, we also show that if you sandwich one row between X and Y, later called double-sided hammer, you can actually get even more bit flips or get bit flips earlier, which is interesting. So people have developed a lot of RowHammer patterns after this. Okay, basically we showed that you actually get bit flips. Is there a question?
Yes, I have a question.
Yeah, go ahead.
Shouldn't virtual memory protect you from doing this because you don't know the physical locations of the rows?
Mm-hmm. Well, you can still hammer a row and it goes to through the translation, it goes to a physical location, and then it leads to a bit flip. So you could still cause bit flips in the presence of virtual memory. But if the question you're asking is if an attacker knows the physical location of the rows, then yes, virtual memory makes it harder because there's an indirection, because what's visible to the attacker is the virtual addresses. But attackers are very smart, meaning they can reverse engineer essentially all of those mappings. Does that make sense?
Okay.
Yeah, later works,
Yeah,
there's a lot of work that shows that you could actually reverse engineer or figure out where a row is located, even in the presence of virtual memory. Does that sound good? And you may see some of the papers. If you pick some of the papers, you may see some of these. Yeah.
Just that some of the cells in these rows are flipped, or are all cells?
Not all cells. Some of the only some of these cells are really vulnerable. Yeah. And you can profile a DRAM chip and figure out which ones are vulnerable also. Yeah. Okay. So in the end, this is certainly a robustness issue. Maybe some real workloads are doing it. In fact, when RowHammer people in industry found out that there are some real workloads that do this, even as early as 2012 or so. Not all workloads, but there are some workload access patterns that lead to these bit flips in the field, even though the workload is not an attacker. It's a benign workload. It's just accessing memory, and you get a bit flip, silent data corruption in the workload. So your workload is useless at that point, depending on where you get the bit flip, of course. Or maybe someone else's workload is useless if it's co-located with your workload, right? So that's the robustness problem, basically. So it's not just a security issue, but it's also a robustness issue more generally. Okay, when we first wrote the paper, we said that memory isolation between different memory locations is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. In the paper, we said that the code that we developed can be the code that we wrote and demonstrated as a user-level program can be developed into an attack that hijacks someone's computer. And we envisioned this. We didn't do that, but later work, this Google work from Project Zero, 1 year later, they basically showed that you could actually do this. I will not go through the details of this, but this Google work, for example, showed that you could take over a system by writing a user-level program. And the way they did it is basically they were able to induce bit flips in the page table entries of a program that pointed, of the user-level program that pointed to its own page table. So if you can actually corrupt your own page table that points to your own page table, you could get write access, meaning the access to modify your own page table. Now, if you can modify your own page table, you could do anything to the system, right? Because at that point, you're not a user, because you can change your page table, change your permissions, and you can change your pointers to point to kernel structures, or you can take over the system. It's a beautiful attack. I will not go over it since that's not the major focus of this talk, but you can take a look. Essentially, that's the takeover system. But later works also showed that even if you may not be able to take over a system for whatever reason, because these are probabilistic attacks in general, all of these attacks are very probabilistic. They're not deterministic. You're not guaranteed to execute the attack. But if you try enough times, maybe you actually do what you can actually get what you're looking for. But you can actually use RowHammer to break confidentiality, meaning, or privacy, meaning that you can read data that you don't have access to. So RowHammer can be used as a side channel because there's this data dependence property of RowHammer. You may guess which data is present in a cell by causing RowHammer bit flips around it. You can take a look at it. It's called RAM bleed. You can break out of virtual machine sandboxes, meaning virtual machine may be limiting you from accessing something, but with RowHammer, you can actually go out of that sandbox. You can also corrupt important data, even if you cannot do any of these. You can corrupt some important data. For example, you may corrupt some important weights in a neural network by hammering, and then your machine learning inference can be useless. This could be bad in self-driving cars, for example. You don't want RowHammer to be happening there, or any kind of robustness issue, I would say. Or people have also shown that you can steal secret data, meaning you can steal cryptographic keys or machine learning model parameters, which may be secret data, right, that you guard. So there are a lot of attacks in the literature that, if this was a RowHammer lecture, I will cover, but I'm not going to cover right now. And you can find some of these attacks covered in some of our papers that I will mention. Okay, so basically, this is really a security problem. And one of the hackers in industry said that RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. So I like that analogy. So, okay. So we actually built a lot of infrastructure to understand these issues because I think these are really important to understand, because understanding is important for building better attacks and also better defenses. You can take the hat of the attacker or hat of the defender. Understanding is good for everyone in the end. So these are infrastructures where we have FPGAs. We program the FPGAs to change the memory controller, and the memory controller can be programmed so that we can actually change the commands that are sent to DRAM chips so that we can, for example, turn off refresh. We can do hammering with different patterns. We can reverse engineer everything in the chip. So these are some ways where you can reverse engineer a lot of things. This allows us to test the DRAM chips in ways that you cannot test with a regular processor, because it's a FPGA that we program. Okay, these are the prototypes. You can actually do a lot of programming yourself if you're interested. We may read some papers that use this depending on your paper selections and final paper assignments also. Okay, so these infrastructures really enabled us to figure out a lot of things about RowHammer. This is the original paper. And we wrote actually other papers on it also that I'm not going to talk about. And this is a retrospective. If you're interested in a 2-pager retrospective about what happened in industry, you can take a look at it. So I'm not going to go into a lot of detail, but I want to talk about solution approaches, because solution approaches are interesting. How do you solve this sort of problem? Now, the problem is discovered in the field. The chips are vulnerable. So it's hard to solve that problem without changing the system. At least fundamentally solve that problem without changing the system. So immediate solutions all increase the refresh rates. Well, let's increase the refresh rate of DRAM so that hopefully the attacker cannot fit enough activations within a refresh interval, right? Okay, I see Girai's things moving a lot. This is Girai's animations. Yeah, that's not a good solution, and we've shown that that's a bad solution even in our original paper, but that was a lever you could do, because memory controllers are not that modifiable. Because we don't want to increase refresh. Refresh is not good for anything, right? Right now, my cell phone is refreshing things and it's wasting a lot of energy. If you increase it more, it wastes more energy, and it's not good for performance either. Okay, so basically, creating more robust chips or using error correcting codes, I think these are hard solutions. Although maybe combined with error correcting codes, maybe you have some other solution that could be useful. Physically isolating rows from each other could be a solution, but it's very expensive. And people have shown that it doesn't have very good security guarantees. You need to read the papers for those. I think these two solutions are quite promising. Like whenever you access a row a lot, you figure that out with some counters and then refresh the victim rows, potential victim rows. Who does this? Memory controller, DRAM chip. There's a lot of literature on that topic. And then there are more recent solutions that talk about throttling, meaning identify an aggressor thread and or aggressor row and don't access it for a while, right? Throttle the accesses to it. Of course, you need to do it safely in both cases without causing bit flips. Okay, these are fascinating. I think there's a lot of literature to be had. There's a lot of literature and there's more literature. But I think in the end, it's really a trade-off between cost, performance, power, and complexity. And there are a lot of solutions, which I'm not going to go into. But I think in the end, people are more or less clear today that we need more intelligent controllers to cover for these issues. If the technology is not working well, you need to change the controller so that controller covers up, meaning fixes some of these issues. If you cannot eliminate these issues, right? So we've always argued this, meaning that memory and system should be co-designed together. And this is an earlier paper, even earlier than the RowHammer paper that we wrote that kind of argues that. Technology scaling is not going to go well for many, many reasons. We should really be thinking, have a system-wide rethinking of the memory and do the system memory co-design. And I'm happy to say that after 10 years later, industry is doing that finally. Maybe they're not very open about it. Well, they're open about it to the extent that they write about it in the papers, but maybe they don't say exactly what they do internally. But what they're doing is essentially intelligent memory controllers. This is a paper from ISSCC, which is a major circuits conference in 2023, from SK Hynix, a major DRAM manufacturer. And they basically talk about RowHammer openly, which is good, finally. And they basically said they have an intelligent controller. And the idea here is a little bit costly. We kind of dismissed it as being the first idea one can think of in our original paper. And I still think that way. But, you know, you got to start somewhere. You got to take some baby steps before you take bigger steps as industry. But the baby steps is here, basically, each row has a counter next to it. And this counter counts the number of activations. And if the number of activations are greater than some threshold, presumably, internally, there's a mitigating action taken. Presumably, it's a refresh of potential victim rows. Makes sense, right? It's a costly solution, but now this is inside the DRAM chip. And it's essentially an intelligent controller inside the DRAM chip, right? This is essentially what we envisioned, which is good. But then maybe there could be better ways of doing it. I'm not going to talk about that. So there's still some obscurity, meaning that there's still not good enough description to validate these solutions. So that's a general problem with memory industry. Memory industry does something. Yes, they may write papers about it, which is good. But in the papers, they don't disclose enough to validate, and they never open source these things because this is really core to their business in the end. So I think going to a place where these could be validated in a nicer way would be nice before someone discovers that, oh, this is also vulnerable, because that's what happened with RowHammer multiple times. Okay, there are also other solutions. I wouldn't recommend reading this paper because it's very hard to read. I think Girai may agree. No, not this one, this one, yeah. And then there's, I mean, you can see that other industries developing solutions, also Microsoft and Google, are quite interested in this problem because that affects their data centers, for example. Okay, so finally, this JEDEC standard in 2024, April, I think, somewhere over here. I don't see April. Okay, April here. Basically says that adopted this solution called per row activation counters. So presumably, future DRAM chips will implement this per row activation counters. Now, the question is, does it work? Meaning, is it secure? And this is one of the recent papers that Oh-san in the back led, who's one of the mentors in the course, that essentially looks at the security benefits and also solutions. And in this paper, we show that to some level, this is secure, meaning if you activate DRAM not so frequently, I guess good enough in existing systems, you're secure. But then you may turn the problem into a performance problem and denial of service problem. So if you're interested, I don't know if this paper was one of the papers that we recommended, but this could be one of the papers. I forgot. So basically, our solution is good is always a good thing to ask. And essentially, you may build a solution. This is one solution for making sure people don't pass, right? Is it a good solution? Well, it could be good if you're sticking to that pathway, right? But you got to guarantee that people stick to that pathway. Yeah, this solution may not be very good. So basically the question is, are we now bit flip free in 2024 and beyond? I don't believe so. Meaning, I think there's a lot more to come in this direction. Maybe not exactly with RowHammer, but maybe there are other issues also that are lurking in the system that lead to bit flips. And solutions should always be configured to be good also, right? I said a lot about the solution, right? How do you increment the counters is a problem. When do you decide you take an action? A refresh is a problem, because these are configurations that you need to make based on the characteristics of the chip. And it may be very difficult to configure these solutions. If you configure them too aggressively, meaning you count, and after 5 activations, you say, oh, I'm going to refresh, that's terrible for performance, right? How do you decide when do you do that is a big problem. Okay, but then there are other problems. This is the RowPress phenomenon. Basically, we disclosed it in 2023 ISCA. And here we were interested in finding some other phenomenon that doesn't require high activation count. Meaning if RowHammer is being sold, usually you require a high activation count. But if you can actually have, and maybe the solution is configured to assume that high activation count. But if you have another problem that leads to bit flips by requiring a much smaller activation count, maybe those solutions are not good anymore. Right? That's the idea. And that's the RowPress paper that showed that. Basically, the idea over is very simple. And it's also fascinating in the sense that you don't need to hammer rows. You just open a row, wait for a while, meaning activate a row, wait for a while. And if you wait long enough, you'll get a bit flip. That sounds good, right? one hammer, one activation causes a bit flip. Some cases meaning extreme cases, meaning they're not allowed in the current standard. But we also show in this paper across 3 major DRAM manufacturers that you can significantly amplify DRAMs vulnerable to read disturbance and legal operating conditions. And also it has a different underlying error mechanism than RowHammer, which is very interesting also. So just to give you an idea, this may be one of the papers that we discuss, let's see, depending on your selection. So I'm not going to discuss in too much detail to leave. But basically, this is RowHammer. This is the activation count needed to induce bit flips using double-sided and single-sided. And RowPress, these are the RowPress regime. If you wait for 7.8 microseconds or 70.2 microseconds, you reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude. And the extreme cases that are not allowed by the standard, you just need to do 1 activation. Okay. And we actually developed a real program, how Song and co-authors did this, on a real system to demonstrate this. Basically, this program keeps a row open by keeping on accessing different cache blocks in the same row. And we showed that we were able to induce bit flips using this program when RowHammer cannot induce bit flips, essentially. And later works independently verified that they were able to take over a system. I'm going to mention that. It's always good if later work builds on your work and independently verifies things, right? Validates things. Okay, so we've also combined RowHammer and RowPress. So now you can imagine different kind of patterns, right? Access patterns to DRAM. You could hammer 1 row, hammer 2 rows, but now you have another dimension, not just the number of activations, but also the time of activations. And this increases space a lot. So how do you verify a DRAM chip is not vulnerable? You need to really test a lot, right? Not just the hammering pattern, which already takes a lot of time, actually. The reason RowHammer is very difficult to mitigate in industry is because there are no efficient testing methods for this. If you really want to test, for example, if a chip is vulnerable, or after how many activations a chip is vulnerable, you have to test every single row with many number of activations with a double-sided pattern, presumably, assuming it's the worst case. That's another assumption, by the way. Okay, now if the time is another dimension over here, the testing time grows exponentially because you can actually vary the time on each of the rows that you hammer, right? So hopefully this gives you an idea of the technology scaling problem. And testing usually is a solution to filter out these problems, but it's not a good solution today. Okay, so later work show that you could actually take over a real system using RowHammer and RowPress. And also there are device level works because the phenomenon of RowPress was really not covered in any device level work. So in one of our papers, we actually said that there should be future works trying to figure out why this is really happening. That was kind of beyond our expertise. We had some idea, but later these people actually read our paper and they basically said, okay, we have some way of modeling this, and they basically talk about why this may be happening at the underlying device level. So you can see that this is a very device level, low level work. So I think there's more to come. Meaning, I think we'll discover more of these things. That's both my hope and fear. I hope I should say that hopefully people who don't want to take over systems will discover it before other people who do want to take over systems, right? It's always that way, right? Because if you don't discover it before other people, or if you don't report it, or if you don't make this a well-known problem, then other people will discover it and they won't tell anyone about it while getting access to whatever they want to have access to, right? Okay, so HBM chips are also vulnerable. This is a recent study that Ataberk led that was published at DSN. So because HBM chips are used in machine learning infrastructure today, they became popular, even though these are very expensive and very low capacity DRAM chips. They're high bandwidth. So machine learning models need high bandwidth. So these are used by a lot of machine learning infrastructure. And we've shown that these chips are no different at all because underlying memory array is the same in any type of DRAM. HBM, DDR, LPDDR, pick whatever you want. Inside the device, inside the chip, it's almost the same. Well, I/O circuitry is a bit different because the interfaces are different, but the memory array itself is the same, meaning the cells are similarly vulnerable. Okay, and Girai's PhD thesis is one of the like most up-to-date theses on this topic. Girai's sitting over there. So if you want to talk to these guys, they're all around you. Okay, so basically a key takeaway, I think, is that read disturbance is a technology scaling problem, and finding a good solution to the read disturbance is difficult. And I think it'll become more so. Right now, I think industry touts this per row activation counters as a good solution, but I don't think they're going to be a good solution. Let's see. And our results show that maybe they're an okay solution, but I think the jury is still out. Especially like per row activation counters, I don't think they consider some of the other issues that, and also there are other issues. Okay, we'll talk about that more maybe if you select the RowHammer paper. Okay, just to show you an idea, this is a slide prepared by Ataberk, so you can fault him for the fact that this is not to scale. You couldn't scale infinity to 1, I guess. That's a tough problem. But basically, one of our earliest work, our early work showed that the number of hammers to induce the first bit flip was very high. This is 2012 or so. Those are the times when we did the testing, right? And then it kept reducing. This is at work, revisiting RowHammer. We showed that with double-sided RowHammer, you go to 24K. In the same work with LPDDR4 technology, which is at the cutting edge, smaller cells are closer to each other. You could actually induce a bit flip with 4.8K hammers. That sounds bad, right? You will wait until you see the next slide. And if HC first is 1, meaning number of hammers to induce the bit flip is 1 activate leads to a hammer every time. You don't need to wait. That's bad, right? These HBM results are also pretty low, as you can see, but this is because HBM, it's not as low as this one because I think the technology node of the HBM is higher. Okay, if you take into account RowPress, the numbers are much worse. Meaning in this HBM chip, you get a bit flip after 335 hammers. You need to wait for some time, as you can see, but you can see it. In this DDR4 chip, you need to, if you wait for 7.2 microseconds after every activation, you can cause a bit flip after 380 activations. Not bad, right? So how should the DRAM manufacturer set the counters? Sounds tough. Or should they limit the row active time? Well, that's what people are trying to do. That was one of our solutions. Now, the problem is if you limit the row activation time, you reduce the row buffer locality, because there's a good reason why we have this row. It enables streaming access patterns, and some workloads will suffer. Okay, these are actually even worse numbers. If you are willing to wait even longer, legally, you get a bit flip after 51 activations. These numbers are correct. Okay, fault Ataberk if they're wrong. You know whom to go to. It's a bit surprising it's 51, but I guess it's possible. And this is the worst case, right? This is the worst number we've seen. Okay. Well, which is still legitimate. This is a real DRAM chip. It should not be having any of these, right? Okay, one of the other worrying things is from Girai's paper and thesis. Basically, you may be setting the counters correctly, let's say, magically, somehow you figure out how to do it, which is tough, I think. But even if you set it correctly, this changes over time. Basically, the number of activations to induce a bit flip changes over time, over usage. DRAM chips may be used in the field for 5 years, 10 years, right? The question is, what happens to them? Does the RowHammer vulnerability become worse, right? Sometimes people actually recycle these DRAM chips. When you buy DRAM chips, you may actually get a DRAM chip that's recycled, right? You may actually be getting a real old DRAM chip, which may be much more vulnerable. So Girai in this work showed that basically, in some extreme condition, if you keep hammering for 68 days, ask him why it's 68 days. I guess he was impatient to wait beyond 68 days. These are some experiments that take very long, by the way. I'm just joking, of course, but if you want to do these experiments, you got to have a lot of patience. And you got to have a lot of infrastructure. And infrastructure is not perfect. You have a lot of parallelism, yeah, etc. It's fun, but it's also time consuming. But if you wait that long and keep hammering, you basically, essentially, if there was no reduction in hammer count, you would see the minimum hammer count you see after aging to induce a bit flip to be equal to the minimum hammer count you see to induce the first flip before aging, right? Before 6 to 8 days. But this is not a line. You can see that there are some things that actually are out of the line, okay? So there needs to be more studies on understanding how aging affects these bit flips in general, not just RowHammer or RowPress, but in general, I think. And we don't have that enough, right? If you send some DRAM into space, and if it sticks out there for 20 years, what happens, right? Because aging conditions are even much worse over there. Okay, so this is Guy's paper that reported this, and this is, I thought I had another copy to his thesis. Okay, we have more talks, but I'm not going to talk more about this. Okay, so you may say, okay, DRAM is old technology, and we're not going to have DRAM anytime soon. Good luck. You're stuck with DRAM for some time, I think, at least 5 to 10 years, maybe more. And even if it's a transition to some other technology, it's not going to be right away replacing DRAM, because there's a lot of manufacturing capability that's needed to really manufacture some emerging technology. Even then, even if you assume that you actually transition to some other technology, the grass is not green there. Unfortunately, emerging memory technologies have even worse problems, some of them. Like, they also have read disturbance and write disturbance problems, but some of them have even worse problems like endurance problems. And aging is always a even bigger question, I think, in these technologies. So we've done some work on emerging memory technologies, and I like this area. It's a tough area, but it's good to, I think, keep the perspective. So we're not getting rid of bit flips anytime soon. So we'd better start building really good controllers. And I think this is really the direction that we should be taking in a better way. So I think one of the issues that in industry is processor and memory is so separate from each other, and the interfaces we have designed between processor and memory are so rigid that even the controller, even if you want to design an intelligent memory controller, you have limited information about the DRAM chip. So I think we need to rethink how we actually think about memory and also redesign some of the interfaces. So we have one work coming up at Micro that Atabak is going to present. That was in Hassan's thesis that essentially talks about the self-managing DRAM interface. And the idea is give DRAM some breathing room, meaning some of these actions like RowHammer protection, etc., per row activation counters, if that's what your choice to implement, are much better done by the DRAM manufacturers. But they cannot do much inside the DRAM chip because the mentality we have for these chips is these are dumb devices. They should not be even doing their own functions. They have to be controlled by a master, which is the memory controller in this case, which sits outside the DRAM chip. So if we actually give a little bit flexibility to the DRAM chip, breathing room, in my opinion, which basically says DRAM chip does some internal functions to protect against RowHammer, or to do better refresh, better retention time management, or to do better memory scrubbing, correcting errors internally, etc., once in a while. You need to give it breathing room, because if the memory controller keeps accessing it and controlling it, then the DRAM chip doesn't have time. To give the DRAM chip time, this paper proposes the huge disruptive change, as one reviewer called it, into the DRAM chip, saying DRAM chip basically can respond to the memory controller. Oh, don't bother me for now. If you're trying to access this region, I'm not going to satisfy your request. So I give you a negative acknowledgement. Try it again later. So with this simple change to the interface, actually can enable a lot of functions. And how many times was this paper rejected? 6 or 7?
6.
I think 7, but he thinks 6, so 6.5, let's say. So this paper was rejected 6 times from conferences for nitty-gritty reasons. But one of the reasons was actually people don't want to do that do this sort of thing because this loses control from the CPU to the memory. Well, that's exactly what we want to do. That's the point of the paper. You want to lose some control so that you can do something better in that part of the system, as opposed to this part of the system that has nothing to do with that part, or not enough information about the system controlling that thing, right? So that's the idea. So I think we need to be also more open-minded in how we think about research, right? These ideas may not be implementable right away, but over time, and I think this is actually a really reasonable idea to implement right away, but over time, these ideas may influence things. Yeah. Anyway, I talked a lot about RowHammer again. It's your fault, Tatabek. Okay. Before we take a break, I should say that this is not just memory. People are realizing that data corruption is in CPU logic too. So essentially, intermittent defects can cause silent data corruption. They may be hard to detect or replicate. They may be exploitable. There are some recent papers on this topic from Facebook and Google. These works show that I mean, this is a slide from Google's presentation, I think. They basically show that their cores disobey instructions, meaning they get a bit flip somewhere or they get some error somewhere. As a result, they get a wrong next program counter, for example, or they get some miscalculation, wrong result. You can see that over here without getting any obvious signal. So they call this mercurial cores, and they localize these to local silicon defects. So they're not really soft errors, meaning cosmic ray hitting, for example. These are really silicon defects. Under some conditions, the computation is wrong in the CPU. It could be, for example, maybe at a high temperature, one of the results takes long time to get latched, and as a result, you get a bit flip, right? Or at some temperature. So your critical path is not to cover for the correct result to propagate, and as a result, you get a bit flip. That could be one reason. It could be because of variation, etc., temperature variation. So this has been reported, and there are papers that try to understand it. There's this paper from Alibaba that reports some results, and there are also papers that try to mitigate it with both software and hardware approaches. I think these are real problems also, and I think we cannot ignore these. So the reason this is happening is also, again, technology scaling, because technology has become so small that these things, and also, I should also say that it's not just a smallness problem, size problem, but it's also a complexity problem. The chips we design are very complex. We're not able to validate and verify everything about it. This is also a technology scaling problem if you think about it, right? Technology scaling has enabled us to put lots of stuff in a single chip, and that lots of stuff is not easy to validate. And we add a lot of complexity to achieve heterogeneity. Okay, so I think the takeaway is both memory and logic errors will become worse with technology scaling. These errors will create worse robustness problems. Security is a part of it. And I think we cannot afford to ignore data corruption. This is a great place to take a break. Any questions before we take a break? Okay, let's take a break. Let's be back at 5:26, 17:26, and then we'll see how much we can cover. Probably not to the end of the slide deck. Now it's better. Okay. All good in the back. Okay. So you covered the technology scaling dimension. I'm going to spend some time on system complexity because I think it's important and we need to think more about it. I'm not going to go into the same depth, let's say, on this one. But there may be papers over here or related that could be interesting. So basically, we have quite complex systems today. These computing systems that we design are more complex than ever. And they're becoming more and more complex, both within the chip level and also outside the chip level. There are many hardware components, and some of these are quite complex components. They're harder to design and verify as a result of this. And they're also harder to reason about their operational behavior. Not only correctness, actually correctness is the easier part perhaps, if you want to verify some component or the system. Performance is harder. But you see that even with correctness, we're having problems, right? With RowHammer, for example, or these bit flips inside the CPU. Performance verification is even harder. Energy is even harder. I think security and privacy are similarly hard because there are so many side channels that these complex systems lead to. Essentially, reasoning is hard, and also controlling interactions between different components and avoiding information leakage is also harder. As complexity grows, these all become harder. So complexity doesn't help anything in the end. And one of the and our old methods don't keep up well with new trends and complexity. For example, I mentioned testing, right? Even testing methods. Traditionally, how testing works is you test a component either in a randomized way. So you basically generate some test patterns. And you apply those test patterns and you have the golden output and you compare the result of the circuit to the golden output. Right? And you can apply to each component. You can apply to the entire system. But this works assuming you know all your patterns, right? You have to come up with a set of patterns. And with RowHammer and RowPress, I'm using these as examples. These patterns are kind of broken, right? It's not just whether you apply ones and zeros. It's really where you apply them also, right? Which rows do you apply them? How many rows do you hammer? How long do you keep a row open? So the dimensions of testing really has increased. As you can see, old methods for testing are not keeping up. We really need better methods for testing. So for example, also to detect silent data corruption in CPUs, I had worked on that problem like in 2008, 7, 9, around that time. And we actually wrote some papers. One of them got a best paper award at VTS, VLSI Test Symposium in 2010. And the idea was to really test the cores once in a while. During online operation, the system takes some time once in a while to test the cores rigorously. You could do this testing at high voltage, for example, to kind of stress the system so that you can actually hopefully identify some of these failures before they happen in a real program. Hopefully the test program gets to these failures and takes the core offline or does some other reconfiguration in the system so that you don't see the failure in a real program. That's the idea. This is called online testing. And I don't think we assigned any papers related to that, but you can look at that. So basically, you need new methods to keep up with new trends and complexity. And I think online testing is going to be employed to fix the silent data corruption problems increasingly in processors. But I'm going to pick up, and also verification methods. How do you verify a system to work? You could argue, oh, we do formal verification. There's a lot of papers on that topic. None of these methods really scale to the complexity that we have today. These are paper tigers, but in real life, unfortunately, they don't work. Scalability of formal verification is always a problem, basically. How do you make the paper tiger work on a complex system like the CPUs and GPUs we have today? Good luck. Not easy. I don't know of any method that makes it work today, basically. So verification is another area I think that we need to rethink. Some hardware support can help over there. But I'm going to pick on something else, which is virtual memory, which you may know. Okay, we're going to talk about that. But complexity has been growing a lot. As you can see, this chart ends at 2020, but there might be a better one. And you can see how complex an SoC is today. And this is 2021. And things are becoming even more complex. You can see CPUs, GPUs, other accelerators, different types of things integrated into the same SoC. And there are many different interfaces also, memory interface. I think there's a PCIe interface. So there are many things, but basically display interface. So there's a lot over here, as you can see. It's similar over here also. And we're actually growing complexity in the third dimension as well, more and more. I could keep showing these pictures, but basically I think related to security, processor complexity and features lead to many, in my opinion, endless side and covert channels. These are basically channels where you find out the information not directly, but you find information indirectly. For example, Spectre and Meltdown are recent examples. How many people know about Spectre? Meltdown, kind of, yeah, okay. I mentioned that in DDCA briefly, but we never went into detail. I think in earlier incarnations of this course, we used to talk about that more. But basically, these are side channels that happen because the processor does speculative execution. It has a cache, and it brings data from areas that it's not supposed to fetch, wrong path. And this leads to a side channel, and someone else can figure out some important data that they don't have access to. Let's keep it at that, because you need to tweak the problem. This is a very, very hard to pull attack. It's very probabilistic also, but you could do it under certain conditions. And I think after Spectre and Meltdown, there are many, these are not the first papers on this topic, they're actually older papers on the topic, like multi-threading causes side channels, etc. But Spectre kind of was very well publicized, let's say. As a result, it was big. Meltdown is more like a bug, but I don't think these will go away, basically. Meaning there will be many, many more side channels because complexity is there, and it's very hard to eliminate side channels, right? You do something in the processor, you consume some power, and that power that you consume, it can be correlated to the bit patterns that you're accessing. So someone, if they're extremely careful, after many, many tries, can figure out what data you're communicating, for example. And if that data you're communicating based on the power signatures, and if that data that you're communicating is like some secret data, a private key, for example, well, even internally within the chip, you can find out these things. Then basically your cryptography is broken at that point, right? And I don't think these will go away, and complexity is not going to help any of this. The question is, what do you do about this? I don't know. I don't have a good answer over here, basically. I think these could be important problems. They're hard to pull off, but we need to do something about it. And then also there's the other aspect, which is not just side channels, but more bugs. Because testing is not easily possible, you may have more bugs and unintended behavior, especially with new features and complex interactions. Like we did some work in this area a long time ago. Again, we had a Micro 2008 paper where we basically analyzed the bugs in state-of-the-art processors. And we found out that whenever a new feature is introduced, like virtualization, acceleration at the time, this we're talking about 2006, 2008, that led to a lot of bugs. That part of the processor has a lot of bugs. If you study the errata sheets of the processors, you will see a lot of bugs over there. And these keep happening. And over time, these bugs do not get solved. If you look at the errata sheets of recent processors, they're pretty long. And they're pretty vague. They won't tell you exactly what the bug is because they don't want you to reproduce it clearly. But they also want to be not legally liable. They said, oh, okay, here's the errata. We know about this. And some of these bugs are not going to be fixed. It basically says in the errata sheet, there's no fixed planned. So these could actually cause security issues, I think. If you can figure out how to exploit these somehow, they could be security problems. They could be safety problems. They're essentially robustness problems again. Because under some condition, this may get triggered, right? And that condition may be fatal. Okay, so basically, how do we tame the processor complexity and resulting issues? Again, I don't have a broad answer, but I want to raise the question over here. I'm going to pick on the access control and protection mechanisms that we have today, because this is an area that has not changed a whole lot. Basically, these access control and protection mechanisms are based on virtual memory today. Whenever you want to have a memory access, you have a virtual memory mechanism. It doesn't do only translation. It also does basically access control and protection, right? And this hasn't changed much after decades of technology scaling and memory system improvements. So a lot has changed over decades. Our systems are more complex. Our memories are huge. In fact, some programs just fit in memory. Why do we have virtual memory in some cases? We have heterogeneous systems, different types of processors accessing memory, different types of memories together on the same SoC. And not much has changed in virtual memory. So it's good to question this, I think. I think this caused a lot of issues, right? Basically, there's a lot of work that shows that virtual memory causes large performance problems and is responsible for large complexity, power, and energy in existing systems because it's invoked in every single memory request, basically. And it's poor for fine-grained security and access control. So you normally do security and access control at a coarse grain with virtual memory, page level, right? Meaning the page is 4 kilobytes, 8 kilobytes, 1 megabyte, 1 gigabyte, whatever it is. Right? And this, if you really want to have finer grained access control, which may be useful for actually preventing some of the side channels potentially, right? You don't want to access, you don't want to provide access beyond the boundary of a data structure, for example, right? Because the other stuff in the page should not be accessed, right? And your data structure ends here. And that's more fine-grained because data structures usually don't align with pages in general. It could be byte granularity or bit granularity if you push it too hard. So it is very poor. This page granularity doesn't map very nicely with the higher level security constructs we have. And also, I think virtual memory hinders innovation in heterogeneous systems and new architectures because you have to, it's something else you have to take into account because programs are written with virtual memory assumption. Whether or not it is good or is useful in today's systems, this needs to be re-examined, I think. But whenever you add an accelerator to the system, the question is always, does it support virtual memory? Right. If it doesn't support virtual memory, existing programs won't work. So you have to do something else, meaning you have to use physical memory, for example, or do something else. So GPUs, for example, didn't have virtual memory for a long time, right? And now they have kind of virtual memory, I guess. New architectures, processing near data. If you want to push computation to the memory side, do you really have the same virtual memory mechanisms on the that you have on the processor? So it basically hinders a lot of innovation. So I think it's been time to rethink virtual memory for a really long time, but it's more than ever right now. If you had taken DDCA, this is one of the slides that I had in DDCA in the virtual memory lecture. I think probably the last lecture actually in DDCA, lecture 26. And I said that virtual memory is actually one of the most successful examples of a lot of things we studied in that course. It provides architectural support for programmers. It partitioned the work between hardware and software in a kind of okay way, maybe. It is an example of hardware-software cooperation. It also is an example of programmer-architect trade-off, right? Meaning the programmer doesn't need to do anything. They don't need to consider the size of memory. They don't need to consider other programs running in the machine. And they just program, and the code is relocatable by the operating system, et cetera. And basically, architects and system designers do the hard work, right? Now, going forward, it's not clear if this should be done the same way. Because I think one of the reasons, but one of the reasons why virtual memory was developed, one of the major reasons is physical memory size was small, and people wrote programs that wouldn't completely fit in physical memory. And as a result, they needed to manage that physical memory. They need to manage bringing data. That part is, I think, gone mostly. Meaning, I don't think we have small physical memory sizes today. If you're the only program running in the system, most of the programs fit. If you are actually putting a lot of programs, if you're doing consolidation, yes, you may run out of memory, of course, but maybe there are other ways of handling it, right? Maybe we don't need to have every single memory request penalized to cover for this case. Right? So it's good to, I think, rethink, basically. Again, I don't have a solution. I'm just suggesting that we should really think. And then there are also hybrid physical memory systems. Do all of them need to go through virtual memory? There are many accelerated systems. We talked about that. Virtualized systems. This actually exacerbates the virtual memory cost a lot. If you have multiple layers of virtualization, people have shown that this is actually, there's virtual memory and then there's a virtual machine underneath it. So there are multiple levels of translation that happens. And then there's local and remote memories. So how far do you take virtual memory, right? If you have remote memory, if you have access to some, let's say, huge amount of memory pool, disaggregated memory, which may become actually even more doable with interfaces like CXL, Compute Express Link, do you virtualize that also? Right? Does it really make sense to virtualize? There are many questions over here. And we already talked about near data accelerators and processing in memory systems. So I think we need to rethink. That said, I'm not going to prescribe any answers at this point, but we have some papers on the topic. I like this direction. This is a rethinking of virtual memory, and I think we need to do more in this direction. And there are more recent papers that look at doing better virtual memory, reducing its overheads without changing the paradigm. I think both are good, especially if reducing the overheads doesn't come with little tweaks. It's good to have big ideas to reduce overheads. So Victima and Utopia are papers. So this is a paper that basically says, oh, not every access should go through costly translation, because if you look at the translation mechanisms that you have today, they're actually very long latency. If you get a TLB miss, if you add in the TLB, you reduce latency, of course. But if you get a TLB miss, there needs to be a lot of complexity and latency to do a page table walk. And basically, this paper says that we should have that when it's needed, and we should have something much simpler when the characteristics that are provided by this very flexible translation mechanism are not needed. For example, if you don't have page sharing, then you may not really need this flexible address translation mechanism, right? So if you're interested, you can take a look at it. Okay, any questions? I can pick on virtual memory more, but we don't have that much time. I actually spent more time than expected. Okay, so now let me focus on the last part. I don't think we can finish this last part, but I think this is also very interesting. New architectures and technologies are always good to examine, regardless of security or not. Even if you don't care about security, we should really be examining new architectures and technologies. But since this talk was more focused on security and robustness, these architectures and technologies can have large impact on security and robustness as well. And I think they need to be designed with system security in mind, maybe ideally as a first-class design goal. Usually, these things are not first-class design goals, robustness, security. They should just work, but they need to provide high performance, right? Or low energy consumption. Even energy was not a design goal for a really long time. It became a design goal in late 1990s when people figured out that, okay, we cannot power these chips with the power budget, with the power supplies that we've been designing essentially, or low cost power supplies, I should say. You can always power something with high cost, right? Okay, and I think there are multiple new technologies and architectures. Accelerator-based computing is already happening. I think there are many accelerators that will keep putting in. Processing in memory is something that I'm going to talk about because I believe in it and I think it should happen, and I think it's happening. It should happen more and more. Emerging memory technologies, I mentioned that earlier. I think that's very important to investigate. I have a quantum computing here that's also good to investigate, but I have a question mark over here because it's another area that's a bit hyped up in my opinion. I think it's very good to investigate, especially at the physics level, etc. But it's not clear if this paradigm will be very general purpose enough. It could be another accelerator. I can imagine a quantum accelerator in the system potentially. But quantum computing for doing everything is not clear at this point. Maybe we should read some papers. Yeah. So that's why I have that question mark. But I think it's good to investigate. Maybe there are other paradigms over here. I actually think biological computing is really important to investigate. Like using the cells to do computation, for example, using the cells as circuits. There's some work in that area. Or using DNA to do computation. There's also work in that area. Not just storage, but really computation itself. There's actually really fascinating. Or using chemical characteristics to do chemical computation, right, as opposed to electronic computation. These are actually really, really interesting areas and fascinating. I didn't put them on this list. They don't get as much hype as quantum computing does today. But I think they're actually, especially the biological part, is really, really interesting and important. If people are interested in that area, talk to me. Okay. Because, I mean, if you look at the nature, it's all about biological computation, right? We're all biological computers. We're also electrical computers, but we're also biological computers. Okay, let me talk about processing in memory without going wilder. I think maybe you've seen some version of these slides at some point, but computing is bottlenecked by data, and we are having problems basically. We have more data, we need more processing. As a result, these model requirements are growing and computation requirements are growing. And we're generating more and more data. I'll go through relatively quickly because we've kind of discussed some of these. So we want high performance, energy efficiency, and sustainability all at the same time. But we're not designing our systems to actually achieve that from the ground up, right? If you took DDCA, one of the things I preached over there as a good architecture is balanced design, right? The system should be balanced when you design a system, right? But immediately we violate that principle. The systems that we have are not balanced. meaning they're very processor-centric. As a result, data moves a lot in our systems, and there's a bottleneck, and that bottleneck is the memory bottleneck. So clearly we can teach these things in classes, but we violate those principles immediately after we teach them. And that's very, like, this causes a big cognitive dissonance in me, which is really annoying. We should be designing systems in a much better way, like we are preaching, I think. And I think the preaching is right in this case. Like, you should really balance the thing so that you get the highest efficiency and highest performance, and you don't get bottlenecked by any component, right? Ideally. Okay, so we want essentially high performance, energy efficiency, and sustainability all at the same time. But yeah, right now we're moving data around. As a result, energy is wasted a lot, performance is lost a lot, and we increase the complexity in our systems to overcome that performance loss. So those systems are complex partially, well, in good part actually, because of data movement, right? If you look at a large fraction of the chip, it's caches, memory hierarchy, memory controllers, interconnects. It's all about data movement. In fact, Intel has recently added, I don't know what they call this, DPUs. Is it called data processing unit? Essentially doing more data movement, etc. Basically data processing. So we keep adding this stuff. Really patching or trying to patch the problem. It's causing more complexity in the system, which is bad for other reasons that we talked about. And it's also causing even more energy waste because these things that we add to the system actually don't work very well. And when they don't work very well, they consume energy even more. So we're in this vicious cycle. So basically, we're very processor-centric. All data is processed in the processor at great system cost. But we know that actually memory is a big bottleneck. People have seen this a lot. I'm going to not go through this, but this is a one-page paper which shows that a processor that's a top processor at the time is designed to finish 4 instructions per cycle, but it's finishing 1 instruction every 4.7 cycles, clock cycles. Not good. This is my PhD thesis. In my first paper, we worked together with Intel and showed that basically the processor, the cutting edge processor that Intel used to design at the time is waiting for data most of the time. And this is Google in a similar paper in 2015. They showed essentially the cutting edge processor that they use in their data centers across all of their workloads is waiting for data most of the time. If you look at energy, the problem is even worse. Memory access is much more costly than an arithmetic operation in terms of energy. You can see that there are 2 to 3 orders of magnitude. This is because technology scaling went really well for logic and not good for interconnect. So over 70 years of technology scaling, well, until Dennard scaling maybe, the transistor performance has improved a lot, but interconnect performance didn't improve as well. Okay, and if you look at less complicated operations than integer add, the disparity between the energy consumption of that and a memory access is much higher. And today actually people are trying to reduce the precision of operations, right? If you look at latest GPUs or any kind of machine learning accelerator, they introduce 4-bit precision. Not even 8-bit, they go to 4-bit. They try to actually go even lower, 2 bits, 1 bit. One of the reasons is energy, right? If you actually if you have large units, you need to bring more data. And also the unit itself spends more energy. So if you actually reduce the precision from 32 bits to 2 bits, you actually get a big cut in both. But if that cut happens, then the data moment energy is still even higher, right? Okay, so that's why we've been doing a lot of studies in this direction and trying to understand the cost of that energy, cost of that data moment on the system. And this is one example where we show that more than 60% of the total system energy spent on data moment on important workloads like YouTube, or video encoding and decoding to be more precise, web browsing, and also TensorFlow inference, machine learning inference in this case. And more recently, we've done more studies with Google to show that more than 90%, or that show that more than 90% of the total system energy is spent on memory in large machine learning models. And this is one example from that study where we show that large machine learning models that are used in edge devices, it could be a phone, for example, LSTMs and transducers, spend most of the energy on DRAM and off-chip interconnect because they keep accessing data. The on-chip buffers are not large enough, they keep accessing data. And if you actually do more memory-centric computing, if you offload some of the machine learning or some of the layers, model layers, to processors or accelerators, not processors, specialized accelerators near memory in a 3D stacked memory chip in the logic layer, you get about 5x energy improvement, as you can see over here on these large models. On average, you get about 3x, but on these large models, you get even more because they're more bottlenecked by memory. Okay, basically the fundamental problem is processing of data is performed far away from the data. And as a result, we're wasting a lot. So processing in memory tries to shift the paradigm to a paradigm that enables computation with minimal data movement. Essentially, it gives the option to do computation everywhere else, and also including the processor. Basically, why don't we have computation capability everywhere? Hopefully, that computation capability will be enabled by an intelligent orchestration mechanism, which may be the programmer, compiler, runtime system that decides what should be executed where. Right? If it makes to execute something in the sensor, execute it there, and then communicate the little result to somewhere else. If it makes sense to execute something in storage, execute it there, and then communicate the little result somewhere else. So if you think about this, then it's a distributed system. And if you push this forward to the extreme, then every component is a distributed agent, and computation happens with coordination across these agents, right? So you can partition your program nicely across these agents. Or you could actually think about a less extreme system where every component is an accelerator, right? And then you still have a central processing unit that distributes tasks to those accelerators, as opposed to having a completely decentralized system. I like thinking about the decentralized system also, but it's probably less likely to happen in the near future. Okay, so we want to make computing architectures more data-centric, meaning that we want to actually process data where it makes sense, enable that capability. So we're going to think about memory as an accelerator in the works that I'm going to mention soon. But there are many questions over here, many system level questions, many architectural level questions, many algorithm level questions, basically many questions that span the entire stack. We're going to look at memory and storage especially, and enable computation capability over there. And for example, if the processor can ask the memory, can I execute this function on you? And the memory says yes, and returns the results. That sounds good. Today, you don't do that. Today, processor says, memory, give me the data one by one, piece by piece, not even large data. You cannot even ask memory for a large amount of data, right? You get 64 bytes. You cannot say, memory, give me this row. Even that thing is not possible. This is really, okay, I'm going to call it stupid. It's stupid in my opinion. If you actually ask this question honestly to someone who doesn't know much about systems, this is what I'm doing, is it right? Maybe they'll say stupid, right? I think it's good to have some honest answer sometimes. Okay, but basically there are many questions over here. How do you design the memory and the controllers to be compute capable? How do you design the processor and communication units? How do you design the software and hardware interfaces to enable this? How do you design the system software compilers and languages to take advantage of this nicely? How do you design the algorithms to fit the underlying architecture and the devices nicely? And also, how do you rethink the computing theory to really understand and have a theoretical basis for doing this? So if you think about computing theory, how many people here have taken an algorithmic complexity course? Okay, you know about big O, big theta, all of those notations, right? What did you do with those things? Well, you clearly use the big O notation to quantify algorithmic complexity of an algorithm. But what you do in those things is you count operations, right? You count how many operations do I do at an order level, of course, not exact number level. And that gives you an idea of the complexity of an algorithm. But maybe I don't care, in the sense that maybe that's not the important thing, right? Maybe the important thing is really not how many operations you do, but how efficiently you do those operations, right? Because a lot of the systems today are bottlenecked by data movement. Maybe that should be part of that computing theory, right? Unfortunately, this is not developed over the course of 80 plus years of computing theory. I hope some computing theorists get excited about it, because I'm not touching that part. Not now at least. Yeah. I wish computing theorists get excited about this, as opposed to some not so interesting problems, maybe, for me, from my perspective, of course, right? Maybe that's interesting for them. Okay. Okay, so I think there are two types of processing in memory in terms of its nature. We have only 5 minutes, so I'm going to cover everything in 5 minutes. One is processing near memory, which is shorter term and easier to do. It doesn't change the paradigm as much. And the other is processing using memory, which changes the paradigm a lot. And I'll give you the differences very quickly. So you have logic and you have memory. Today you design them separately. Logic could be a CPU, GPU, or a piece of it, but it's designed separately from the memory, right? Processing near memory says you take that logic and put it closer and closer and closer and closer to memory. You can tightly integrate it with some emerging technology like logic layer and the memory layers. You can put it inside the memory chip. You can put it next to each subarray, next to each cell, but you still design logic and memory separately. That's the key over here, meaning that you don't change anything in their individual designs. Okay, this is easier to do because it doesn't change the paradigm a lot. This still has adoption issues because the fact that computation is done beyond the processor chip has some implications on the software and also a lot of other things that we use to design our systems. But processing using memory is fundamentally different in terms of nature. You have processor, not processor, logic, and then you have memory. Now forget about logic. I don't care about logic, let's say, but I have memory. Now I'm going to think about this memory as a computational device, and every memory has some analog operational characteristics that lead to some functions. So you can actually use the memory functions to do computation. So you could do bitwise AND, or not, matrix vector multiplication, depending on the memory type and its characteristics. These are in the analog domain. Does that sound good? Now this changes the paradigm a little bit because now you don't design the logic as it is. You just think about memory, and logic is implemented using memory. Okay. Okay. I won't have time to talk about a lot of these, but my intention was to really cover the different aspects. But before, maybe we'll continue next week with the remaining part of the slides. But today, near memory computing or processing near memory is really happening. Basically, there are some emerging technologies that are 3D stacked. You can have a logic layer and you can put processing in the logic layer. I think this will happen more and more. But more recently, people have been designing, it's a startup in France, UpMem, and then Samsung, Hynix, Alibaba. They've been all designing DRAM chips where there's logic or processor or accelerator next to each DRAM bank. Essentially, next to each DRAM bank, you have a processor. In UpMem's case, it's a multiple instruction, multiple data, or multi-threaded processor that you can program using a version of C++, let's say. So it's programmable. Not bad, I would say. There's some idiosyncrasies, but if they get rid of these idiosyncrasies, this could be even better. And in Samsung, SK Hynix, and Alibaba's case, there are DRAM chips where you have accelerators tailored toward machine learning. You can do matrix multiplication, for example, or multiply and accumulate operations, essentially, in accelerators next to each DRAM bank. And their goal is to really accelerate operations as opposed to offload large kernels like UpMem does. This is more general purpose. These are more special purpose. And then you can have things like FPGAs. Here, there's an FPGA over here next to a lot of memory modules over here. It's a board. And in this FPGA, you can actually have any logic, but these folks from Samsung and Meta had logic for recommendation inference. Essentially, they wanted to accelerate that because it's a very data-intensive task. And then there are interfaces that enable you to do off-chip also. This is Compute Express Link interface. This is a paper from SK Hynix. So we're going to see some of these papers, maybe, depending on your selections later on. And I think there is even more opportunity with 3D stacked logic and memory going into the future because over time, these technologies will develop better. And as a result, we will be able to put true logic layers, very good logic layers underneath memory. And then we can put computation over there. Sounds like the perfect time to stop. Okay, if there are no questions, we're done. Otherwise, we're going to pick up from here next week. And hopefully you'll make your selections and submit your homeworks. I don't see any questions. Okay, we'll see you all next week then.